The morning of March 17, 1943, brought nothing but tension to the Daimler-Benz technical facility outside Stuttgart. 3 senior engineers from the aircraft engine division stood in a workshop that smelled of machine oil and metal shavings, staring at something that had arrived 2 days earlier on a flatbed truck from North Africa. The object on the work stand looked battered, scarred by combat and sand erosion, but intact enough to tell its story. An Allison V-1710 engine, serial number stamped into the crankcase, pulled from a downed Curtiss P-40E Warhawk somewhere in the Tunisian desert. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engineers had requested this engine specifically, not because it represented cutting-edge German intelligence gathering, but because Daimler-Benz needed answers to questions that had been quietly troubling German aviation planners for months. American fighters were appearing over North Africa in numbers that shouldn't have been possible, production rates that defied German industrial calculations. And now here was the evidence: an actual American aircraft engine, waiting to be disassembled and understood. What the Daimler-Benz team discovered over the next 6 weeks would force a fundamental reassessment of American industrial capability. The technical report they produced, stamped with the classification markings of the Reich Air Ministry, documented something more significant than raw specifications or horsepower figures. It revealed a design philosophy, a manufacturing approach, and an industrial strategy that Germany had neither anticipated nor prepared to counter. The realization that emerged from that analysis was stark and uncomfortable. The Americans weren't just building engines differently. They were building them from a completely different understanding of what industrial war would require. And by 1943, Germany was already 5 years behind in learning that lesson. The immediate question facing German aviation engineers in early 1943 was simple but urgent. How were the Americans producing fighter aircraft at rates that seemed to exceed anything Germany had projected? Intelligence reports from North Africa documented P-40 Warhawks, P-38 Lightnings, and P-39 Airacobras, appearing in theatre with a consistency that suggested vast production capacity. The Luftwaffe had shot down dozens of these aircraft, had studied their tactics, had developed counters to their operational employment, but nobody had seriously examined what made the aircraft possible in the first place: the engines. By March 1943, the Reich Air Ministry's Technical Intelligence Division had accumulated enough captured American equipment to warrant detailed analysis. The Allison V-1710 represented something both familiar and foreign to German engineers. Familiar because it was a liquid-cooled V-12, the same basic configuration as the Daimler-Benz DB601 and DB605 engines powering Messerschmitt Bf 109 seconds and Bf 110 seconds. Foreign because every detail of its construction revealed priorities and assumptions that didn't match German practice. German aircraft engine development in 1943 operated from principles established in the mid-1930s. Daimler-Benz had begun work on the DB600 series in 1929, following guidelines from the Reich Ministry of Defense that called for a liquid-cooled inverted V12 inches, the 30-litre class. The resulting engines were technical marvels, sophisticated machines that pushed the boundaries of metallurgy and precision engineering. The DB601, which entered serial production in November 1937, featured direct fuel injection, a hydraulically controlled variable-speed supercharger, and construction tolerances measured in thousandths of a millimetre. Approximately 19,000 DB601 seconds were built before production shifted to the DB605 inches, 1942. The 605, with its increased bore and displacement, delivered 1,475 horsepower and represented the cutting edge of German aero engine design. These engines powered the aircraft that had won air superiority over Poland, France, and the Low Countries. They had proven themselves in combat, validated German engineering philosophy, and seemed to demonstrate that precision manufacturing and sophisticated design were the keys to air power. But precision manufacturing required time, skilled labor, and resources that were becoming increasingly scarce as the war expanded. The Allison V-1710 had followed a different developmental path. The Allison Engine Company, a division of General Motors since 1929, had begun developing an ethylene glycol-cooled V12 engine to meet a U.S. Army Air Corps requirement for a modern 1,000 horsepower engine. The target was straightforward: build an engine that could power a new generation of streamlined bombers and fighters, and do it in a way that allowed mass production without requiring German-style precision machining for every component. The V-1710C6 successfully completed the Army's 150-hour type test on April 23, 1937, at 1,000 horsepower. It was the first engine of any type to pass this test. But what made the achievement significant wasn't the power output or the test completion. It was the design philosophy that made that test possible. General Motors brought automotive manufacturing principles to aircraft engine production. The V-1710 was designed around what engineers called a long block, a core assembly of cylinders, crankshaft, and basic internal components that could be mass-produced to consistent standards without requiring master craftsmen for every step. The front and rear of this long block were modular, different. Propeller reduction gearing could be attached at the front depending on aircraft requirements. Different supercharger configurations could be mounted at the rear. The same basic engine could be adapted to fighters, bombers, or experimental aircraft simply by changing the accessories attached to the core unit. This was automotive thinking applied to aviation. Build the hard parts, the precision components, to exacting standards once, then make everything else interchangeable and adaptable. German engineers understood modular design in theory, but the Allison's implementation revealed how far that concept could be pushed. The V-1710 had 12 cylinders arranged in a 60-degree V configuration with a bore and stroke of 5.5 inches by 6 inches, giving a displacement of 1,710.6 cubic inches, or just over 28 litres. The valve train used a single overhead camshaft per bank and 4 valves per cylinder, similar to German practice. But the similarities ended at the basic architecture. The Allison's construction revealed systematic choices made to favour production volume over individual engine perfection. Steel cylinder barrels were screwed and shrunk into cast aluminum alloy blocks, a technique that saved weight and simplified manufacturing compared to German methods that required more complex assembly processes. The dry liner system, where cylinders projected beyond the block and were secured by threaded rings, eliminated the need for multiple hold-down studs and reduced the possibility of distortion during installation. Every bearing, every gasket, every bolt on the V-1710 was designed to be installed by mechanics with moderate skill rather than master craftsmen. The engine manuals, which the Daimler-Benz team obtained along with captured hardware, revealed another difference. American technical documentation assumed that maintenance would be performed by young men with basic mechanical training, not by specialists, who had spent years learning the intricacies of precision German equipment. The instructions were straightforward, the tolerances were wider than German practice allowed, and the entire design seemed to prioritize keeping engines running under field conditions rather than achieving maximum theoretical performance in ideal circumstances. This was the first uncomfortable realization. The Americans had deliberately chosen a different optimization point. Not maximum performance per engine, but maximum operational capability across thousands of engines maintained by an army of moderately trained mechanics. The Daimler-Benz engineers began their detailed analysis by disassembling the captured Allison following standard German technical evaluation procedures. Every component was measured, weighed, photographed, and catalogued. The crankshaft received particular attention. This was the heart of any reciprocating engine, the component that converted the up and down motion of pistons into rotational power. German crankshafts were precision-forged components requiring extensive machining and careful balancing. The Allison crankshaft was a revelation. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. It was a massive piece, robust beyond what German design would have specified for the same power output. The counterweights were larger and heavier than necessary by German calculations. The bearing surfaces showed wear patterns that indicated the engine had operated for several hundred hours before being shot down, far longer than early German intelligence had estimated for American engines operating in desert conditions. But what struck the engineers most was the simplicity of the manufacturing approach. The crankshaft wasn't trying to be the lightest possible component that could survive operational loads. It was deliberately overbuilt, using extra material to ensure reliability rather than optimizing for minimum weight. This added roughly 50 pounds to the engine's dry weight compared to an equivalent German design, but it also meant the crankshaft could tolerate manufacturing variations, installation errors, and operational stresses that would have damaged a more highly optimized German component. The reduction gears told a similar story. The V-171039 used external spur gears to drive the propeller at a reduced speed relative to the crankshaft. German engineers favored more compact internal gearing systems that saved space and weight. The Allison's external gears were heavier, took up more room, and required their own lubrication system. But they could be inspected without disassembling the engine, replaced in the field if damaged, and manufactured on standard gear-cutting equipment rather than requiring specialized tooling. The supercharger drive system revealed the most significant philosophical difference. German engines like the DB601 used a sophisticated hydraulic clutch system to vary supercharger speed, allowing precise optimization of boost pressure across the aircraft's altitude envelope. The Allison used a simpler, more robust system with less precise control, but far fewer components that could fail or require adjustment. The German system was elegant, efficient, and required skilled maintenance. The Allison system was straightforward, durable, and could be serviced by mechanics who understood basic mechanical principles. When the Daimler-Benz team calculated the manufacturing time required to produce each approach, the difference was sobering. The German hydraulic system required approximately 40 hours of skilled machinist time. The Allison system required 12 hours using mostly semi-skilled labor. Multiply that difference across 10,000 engines, and the implications became clear. The Americans could produce nearly 3 engines in the time Germany needed to produce one, not because American engineers were more capable, but because American design priorities were fundamentally different. The spring of 1943 was bringing this reality into sharp focus across multiple fronts. In North Africa, American forces that had landed as part of Operation Torch in November 1942 were advancing east to link up with British 8th Army forces, pursuing Rommel's Africa Corps west from Egypt. The air war over Tunisia had become a grinding campaign of attrition, with both sides throwing fighter aircraft into daily combat. Luftwaffe pilots flying Messerschmitt Bf 109Gs and Focke-Wulf W192s had generally proven superior to the American P-40 Warhawks in individual combat. The P-40 was slower in a climb, less maneuverable in a dogfight, and suffered from the Allison V-1710's weakness at high altitude, where the single-stage supercharger couldn't maintain sufficient boost pressure. German combat reports documented this consistently. P-42s could be outflown, outmaneuvered, and shot down by competent Luftwaffe pilots flying aircraft powered by DB605 engines. But the P-42s kept coming. Every day brought more American fighters, shot down 3 P-42s on Monday, face 5 on Tuesday. The replacement rate seemed impossible. The 57th Fighter Group, which had reached the Western Desert in August 1942, had suffered heavy losses through the El Alamein campaign and the advance across Libya. Yet by March 1943, the group was still operational, still flying missions, still putting P-42s into the air over Tunisia. The 33rd Fighter Group had taken part in Operation Torch with 76 P-42s. By February 1943, only 13 of the original aircraft remained, but the group hadn't been withdrawn from combat. It had been resupplied, re-equipped, and was back in action within weeks. This pattern repeated across the theatre. Individual American aircraft might be inferior to their German counterparts in specific performance categories, but American logistics and production capacity were compensating for tactical weaknesses. The Daimler-Benz engineers studying the captured Allison were beginning to understand why. The engine on their workbench represented a different industrial philosophy. German engines were crafted, American engines were manufactured. The distinction mattered more than German planners had realized. Consider the production statistics that were available to German intelligence in early 1943. The Allison Engine Company had produced its first Wohn 1710 inches, 1931. By 1940, production had ramped to modest numbers, as the P-40 Warhawk began entering service. But by 1942, Allison was producing over 700 V-1710 engines per month. By 1943, that number would exceed 1,000 per month. Over the course of the war, more than 70,000 V-1710 engines would be built. Germany, by comparison, had produced approximately 19,000 DB601 engines over 6 years of production before shifting to the DB605. The DB605 would eventually reach production numbers of around 42,400 units, impressive by any measure. But achieving those numbers required Germany to dedicate massive resources to aircraft engine manufacturing, resources that were being stretched thinner as Allied bombing campaigns began targeting German industrial facilities. The Allison's design allowed production to scale up or down based on available capacity without requiring fundamental changes to manufacturing processes or retraining of workers. This was the insight that emerged from the Daimler-Benz analysis. The V-1710 wasn't designed to be the best engine possible. It was designed to be a good engine that could be built in enormous quantities by workers who didn't need years of specialized training. Every design choice reflected this priority. Wider manufacturing tolerances meant more parts could be accepted from suppliers without rejection. Modular construction meant different factories could build different components without requiring complete engine assembly capability at every location. Simplified maintenance requirements meant engines could be kept operational in field conditions by young mechanics who had received a few months of training rather than requiring specialist technicians. The German approach had produced technically superior engines that performed magnificently in the hands of skilled maintenance crews working under good conditions. The American approach had produced technically adequate engines that could be maintained and operated under terrible conditions by inexperienced personnel and still complete their missions. The more the Daimler-Benz team examined the Allison, the more they recognized design features they had dismissed or considered unnecessary. The oversized oil sump that added weight but ensured adequate lubrication even when the aircraft was operating in extreme attitudes. The robust engine mount points that were heavier than minimum requirements but could tolerate rough handling during installation and removal. The simplified electrical system that sacrificed some precision but could be diagnosed and repaired with basic test equipment. Every one of these design choices made sense when viewed through the lens of mass production and field maintenance. None of them represented technical ignorance or inferior engineering capability. They represented a different understanding of what industrial warfare would require. And by 1943, that difference was beginning to matter on the battlefield. The Luftwaffe could shoot down American aircraft. German pilots were generally better trained. German aircraft often had superior performance characteristics, and German tactics had evolved through years of combat experience. But Germany couldn't replace losses at the rate the Americans were replacing theirs. The production gap was becoming an operational problem that tactical excellence couldn't solve. This was what the captured Allison revealed. Not just the specifications of one engine type, but the industrial strategy behind American aircraft production. The numbers were beginning to tell the story. In 1943, the United States would produce over 85,000 aircraft. Germany would produce approximately 25,000. The disparity in engine production was even more dramatic because American designs required fewer man-hours per unit. The technical report, produced by Daimler-Benz in the spring of 1943, documented these findings in careful detail. The engineers praised the Allison's robust construction and noted its suitability for mass production. They identified the modular design as particularly worthy of study, but the report's conclusions were sobering. Germany's aircraft engine industry was optimized for building sophisticated, high-performance engines in moderate quantities. America's aircraft engine industry was optimized for building reliable, maintainable engines in massive quantities. Both approaches could produce successful aircraft. But in a prolonged industrial war, the American approach had a fundamental advantage that German manufacturing couldn't easily counter. The realization came too late to change German production systems. By 1943, Germany's industrial capacity was already committed to existing designs and manufacturing processes. Retooling to adopt American-style modular production would have required shutting down engine production for months, exactly what Germany couldn't afford with the war intensifying on multiple fronts. The Luftwaffe would continue flying aircraft powered by DB-605 engines, by Jumo 211 and 213 engines, by BMW 801 radials. These engines would continue performing well, continue powering capable aircraft, but they would never be available in the numbers needed to match American production. The captured Allison sitting in the Stuttgart workshop represented more than enemy hardware available for study. It represented a strategic reality that German planners had missed in the 1930s when aircraft engine design philosophies were being established. The Americans had looked at the problem differently. They hadn't asked how to build the perfect engine. They'd asked how to build thousands of good engines with the workforce and industrial base they had available. That question had led to different design priorities, different manufacturing techniques, and ultimately to the modular, robust, mass-producible V-1710. By the time German engineers recognized what the Americans had achieved, the window for adaptation had closed. Germany would fight the rest of the war with engines designed for a different kind of conflict, built by an industrial system that couldn't match American output. The gap would only widen as the war continued. Luftwaffe mechanics inspected, captured Allison V-1710, then admitted. They were 5 years behind. The spring and summer of 1943 brought the full weight of this industrial disparity into operational reality. In the Mediterranean theater, American air power was transitioning from defensive operations to sustained offensive campaigns. The P-40 Warhawks that had struggled to hold air superiority over Tunisia were now being supplemented by P-38 Lightnings and were beginning to receive support from newer aircraft types. Each of these aircraft was powered by Allison V-1710 engines, usually in pairs for the P-38. The Allison's limitations at high altitude remained a tactical problem. Single-stage supercharging meant that P-40 seconds and P-39 seconds lost power above 15,000 feet, exactly where Luftwaffe fighters preferred to operate. German pilots could use altitude advantage to choose when and where to engage, diving on American formations and climbing away before escorts could respond. But the tactical advantage couldn't compensate for the strategic arithmetic. For every Luftwaffe fighter lost, Germany had to produce a replacement from increasingly strained industrial resources. For every American fighter lost, the replacement was already in the pipeline, often already crated and loaded on a transport ship. The production numbers told the story in stark terms. Curtiss Wright built approximately 13,738 P-40 Warhawks before production ended in November 1944. Lockheed built over 10,000 P-38 Lightnings, each requiring 2 Allison engines. Bell built nearly 10,000 P-39 Airacobras and P-63 King Cobras. All of these aircraft were powered by variants of the V-1710. The engine that Daimler-Benz engineers were studying in Stuttgart existed in dozens of specific configurations, each optimized for particular aircraft installations, but all built around the same basic long block. The V-171039 that powered many P-40Es, the V-171049 and -53 that powered early P-38Fs, the V-171063 that powered P-39Ns. Each variant required different accessories, different supercharger drives, different reduction gearing, but the core engine remained essentially unchanged, allowing Allison to maintain high production rates without constantly retooling for completely new designs. This modular approach extended to maintenance and field repair. When a P-40 suffered engine damage, mechanics didn't need to rebuild the specific V V-1710 variant that came with that aircraft. They could install any compatible Allison from available stocks, often pulling engines from aircraft damaged beyond repair and installing them in airframes that could still fly. This interchangeability was built into the design from the beginning, another reflection of automotive manufacturing principles applied to aviation. German aircraft engines, by contrast, were more tightly integrated with their specific aircraft types. A DB605A designed for a Bf-109G had different accessories and mounting configurations than a DB605B designed for a Bf-110G. While components could sometimes be swapped, the process required more specialized knowledge and often more extensive modifications. The practical impact appeared in mission availability rates. American fighter groups operating in North Africa and later in Italy reported that they could keep higher percentages of their aircraft operationally ready despite working in harsh desert conditions with limited facilities. German units operating in the same theater faced increasing maintenance challenges as the war progressed, particularly as experienced mechanics were killed or transferred, and replacements lacked the specialized training that German engines required. The Daimler-Benz report noted this maintenance advantage explicitly. The American engine design philosophy accepted slightly reduced performance in exchange for significantly improved operational reliability and simplified maintenance. This was a trade-off that made sense for an industrial power planning to fight a long war with a conscript force rather than a professional military. It was exactly the kind of trade-off Germany hadn't made when designing aircraft engines in the 1930s. But the most significant finding in the Daimler-Benz analysis wasn't about the engine itself. It was about what the engine revealed about American industrial capacity and planning. The modular design, the wide tolerances, the simplified maintenance requirements, all pointed to a manufacturing system designed to scale to enormous production volumes. The Americans weren't just building aircraft engines, they were building an aircraft engine industry capable of supporting a global war. That industry was already operating at a scale Germany couldn't match. The Allison plant in Indianapolis employed over 23,000 workers by 1943. The facility ran 3 shifts, 24 hours per day, 7 days per week. Assembly lines moved at speeds that would have seemed reckless by German standards, but the simplified designs and standardized components made high-speed assembly possible. Quality control focused on functional testing rather than precision measurement of every component. If a part fit, if it worked, it was acceptable. This wasn't sloppy manufacturing. It was a different manufacturing philosophy. German practice called for each component to meet precise specifications, regardless of whether that precision affected functional performance. American practice called for each component to meet functional requirements, with dimensional specifications loose enough to allow high-speed production. The result was that American factories could produce 3 or 4 engines in the time German factories needed to produce 1 engine of equivalent capability, and American factories were being built at a pace that Germany couldn't even attempt to match. By 1943, multiple American companies were building aircraft engines at volumes that individually exceeded Germany's total production. Allison was producing V-1710 engines. Packard was building Rolls-Royce Merlins under license, designated V-1650. Pratt & Whitney was producing R-1830, Twin Wasps, and R-2800 Double Wasps. Wright was building R-1820 Cyclones and R-2600 Twin Cyclones. Each company operated multiple plants, each plant employed thousands of workers, and all of this production was protected by thousands of miles of ocean from any possibility of enemy bombing. Germany had no answer to this industrial advantage. The Luftwaffe could bomb British aircraft factories, could disrupt Soviet production facilities, but couldn't touch American manufacturing capacity. The strategic implications were becoming clear to German planners even as the Daimler-Benz engineers completed their technical analysis. Individual German aircraft might outperform individual American aircraft, but Germany couldn't produce aircraft fast enough to replace combat losses and also expand the Luftwaffe to meet increasing demands. The Americans could do both simultaneously. By mid-1943, American aircraft production was exceeding German production by factors of 3 to 1 or more, and the gap was widening. This disparity appeared most dramatically in fighter production. Germany built approximately 5,000 Bf-109 seconds in 1943. The United States built over 21,000 single-engine fighters that same year, including P-40 seconds, P-39 seconds, P-47 Thunderbolts, and P-51 Mustangs. The last two types were powered by different engines, the P-47 by a Pratt & Whitney R2800 radial, and the P-51B, and later variants by the Packard-built Merlin V-1650. But many of those 21,000 fighters were powered by Allison V-1710 seconds, and those engines kept the aircraft flying. The V-1710's limitations were real and significant. The single-stage supercharger meant poor high-altitude performance in most installations. The lack of a two-stage supercharger until very late in the war meant that V-1710-powered fighters couldn't match the high-altitude capabilities of aircraft using Packard Merlins, or late-war German, engines with improved supercharging. But the V-1710 worked, and it kept working under conditions that would have defeated more finicky engines. Pilots operating P-40 seconds in North Africa dealt with sand that infiltrated every aircraft system, temperatures that ranged from freezing at night to well over 100 degrees during the day. Maintenance performed in open-air workshops with limited tools and equipment. The Allison engines absorbed this punishment and continued operating. Field reports documented engines running for 500 hours or more between overhauls, far longer than early projections had suggested. This reliability resulted directly from the design choices that German engineers had initially questioned. The wide tolerances meant sand infiltration didn't immediately cause binding. The robust construction meant components didn't fail from thermal stress. The simplified systems meant mechanics could keep engines running with basic maintenance procedures. Every feature that added weight or reduced peak performance contributed to operational reliability. The Pacific Theater told a similar story. American forces fighting across New Guinea and the Solomon Islands operated under conditions even worse than North Africa. Humidity, rain, coral dust, and primitive facilities tested aircraft and engines to destruction. Yet P-38 Lightnings, each carrying two V-1710 engines, operated from forward airstrips carved out of jungle and kept fighting. P-39 Airacobras and P-40 Warhawks likewise continued operating despite conditions that should have grounded aircraft requiring precision maintenance. The Allison's tolerance for abuse became legendary among American ground crews. The engine could lose oil pressure, overheat, ingest foreign objects, and still complete its mission. This wasn't because American engines were built better than German engines in terms of precision and sophistication. It was because American engines were built differently, optimized for different priorities. German aircraft engines in the Pacific Theater, primarily captured examples being evaluated by technical intelligence, proved far more sensitive to environmental conditions. The precision manufacturing that enabled high performance also created vulnerabilities to contamination, thermal stress, and rough handling. This wasn't a flaw in German engineering. It was a characteristic of engines designed to operate in European conditions with professional maintenance support. The Americans had designed for the global war they expected to fight, not the European war Germany had prepared for. By late 1943, the production and operational advantages of American engine design were translating into strategic air superiority. In the Mediterranean theater, the Luftwaffe was being ground down by attrition it couldn't sustain. In the Pacific, Japanese air power was being systematically destroyed by American aircraft that could be replaced faster than Japan could shoot them down. And over Europe, the preparations were underway for a strategic bombing campaign that would leverage American industrial capacity to its maximum effect. The 8th Air Force, building up strength in England, would eventually field bomber formations, escorted by fighters powered by Packard Merlins and Pratt & Whitney radials. But the industrial base that made those later aircraft possible had been built on the foundation of simpler, earlier designs, like the Allison V-1710. The lessons learned in mass-producing V-1710 seconds were being applied to every American aircraft engine program. The workforce trained on V-1710 assembly lines was building the industrial capacity that would produce next-generation engines. The modular design philosophy, pioneered with the V-1710, was influencing American radial engine designs, leading to standardized components across different engine families. Everything learned from the V-1710 program was making subsequent programs more efficient. Germany had no equivalent learning curve to leverage. Each new German engine design was largely independent, requiring unique tooling, specialized training, and custom manufacturing processes. The DB605, the Jumo 213, the BMW 801, each represented sophisticated engineering and capable performance, but none of them shared significant components with the others. None of them could be produced by workers trained on a different engine type without extensive retraining, and none of them could be maintained in the field by mechanics with only basic training. This lack of standardization and interchangeability was becoming a critical weakness as the war progressed. The Daimler-Benz report finished its analysis with recommendations that were never implemented. The engineers suggested studying American modular design principles for application to future German engine programs. They recommended investigating simplified maintenance procedures that could be performed by less skilled personnel. They proposed research into manufacturing techniques that could increase production rates without proportionally increasing skilled labor requirements. None of these recommendations received funding or priority. By mid-1943, Germany's industrial capacity was fully committed to existing programs. There was no spare capacity for developing new manufacturing approaches, no time to retrain workers, no resources to retool factories. The German aircraft engine industry would continue building excellent engines in numbers insufficient to meet operational demands. The gap between German and American production would continue widening until the war's end. The captured Allison that prompted this analysis remained at the Daimler-Benz facility for several months before being transferred to other technical intelligence offices for further study. The engine itself wasn't particularly remarkable by this point. Daimler-Benz had documented everything worth documenting, had photographed every component, had measured every dimension. What remained remarkable was what the engine represented. It was physical evidence of American industrial capability, a tangible demonstration of how far Germany had fallen behind in understanding what modern war would require. The V-1710 wasn't superior to German engines in terms of specific power output, fuel efficiency, or operational altitude, but it was superior in the metrics that mattered for industrial war: production speed, manufacturing efficiency, maintenance simplicity, and operational reliability under adverse conditions. These weren't the metrics German engineers had optimized for in the 1930s. They weren't the metrics that made sense for a nation planning short, decisive campaigns with professional forces, but they were exactly the right metrics for America's approach to global war. The final irony was that German engineers recognized American advantages but couldn't leverage those insights. Understanding that the Americans had made better strategic choices didn't change Germany's strategic position. Acknowledging that modular design and simplified manufacturing were superior approaches didn't magically create the industrial capacity to implement those approaches. The recognition came too late, when Germany's options were already constrained by decisions made years earlier. The war continued with Germany fighting at an increasing disadvantage in aircraft and engine production. The Luftwaffe adapted tactically, developing new aircraft types and improved engines. The DB605 evolved through multiple variants, eventually producing 2,000 horsepower in its most advanced forms. New designs like the Junkers Jumo 213 and the BMW 801 Radial reached production and powered capable aircraft. But none of these developments could compensate for the production gap. American factories continued expanding output. Allison production peaked at over 70,000 engines delivered by war's end. Other American engine manufacturers produced hundreds of thousands more power plants, This torrent of engines powered tens of thousands of aircraft that overwhelmed Axis air forces through sheer numbers. By 1944, the Luftwaffe faced fighter and bomber formations so large that tactical skill couldn't compensate for numerical inferiority. American pilots flying aircraft powered by various engines, including many V-1710 fighters, dominated the skies not because American aircraft were necessarily better individually, but because America could replace losses indefinitely, while Germany could not. The production advantage that began with design philosophies established in the 1930s played out in operational realities through 1945. The men who flew V-1710-powered aircraft rarely knew the technical details of what made their engines different from enemy designs. They knew the Allison was reliable, that it could take damage and keep running, that ground crews could fix problems quickly and get aircraft back in the air. These practical considerations mattered more than specifications or performance charts. The engine worked, and working engines kept fighters flying missions. The Americans who designed the V-1710 never received the recognition that later, more advanced engines received. The Packard Merlin that powered the P-51 Mustang to legendary status overshadowed the earlier Allison designs. The powerful radials that powered B-17 Flying Fortresses and B-29 Superfortresses seemed more impressive. But the V-1710 did its job, powered thousands of aircraft through millions of flight hours, and demonstrated the industrial philosophy that would win the war. That philosophy, more than any individual weapon system, gave the Allies the advantage that defeated the Axis powers. The ability to produce adequate equipment in overwhelming quantities proved more valuable than producing perfect equipment in limited numbers. Germany learned this lesson from the captured Allison engine in 1943. But by then, the lesson came too late to change the war's outcome. The industrial advantages America had built into its designs from the beginning would carry through to victory. The Daimler-Benz engineers who studied the captured V-1710 understood what they were seeing. The technical report they produced acknowledged American industrial superiority in specific terms, but understanding didn't translate to capability. Germany couldn't become America, couldn't rebuild its industrial base around different principles, couldn't undo the consequences of earlier strategic choices. The gap was real, measurable, and by 1943, unbridgeable. Over 70,000 Allison V-1710 engines were built between 1931 and 1948. These engines powered America's first-line fighters through the critical early years of the war, provided the industrial foundation for later engine programs, and proved that American engineering could meet the demands of global conflict. The engines weren't perfect. The single-stage supercharger limited high-altitude performance. The modular design added weight. The wide tolerances sacrificed some efficiency, but perfect was never the goal. The goal was good enough, in sufficient quantities, maintainable under field conditions, producible by semi-skilled workers, and reliable under abuse. The V-1710 achieved all these goals. In doing so, it demonstrated the industrial strategy that would characterize American war production across all equipment categories. Build it simply. Build it robustly. Build it in massive numbers. The Luftwaffe mechanics who first examined captured American fighters didn't initially recognize what they were seeing. The aircraft seemed crude compared to German designs, the engines less sophisticated, the overall construction apparently simpler. But simplicity was strategy, not limitation. The Americans had chosen to build equipment that could be produced at scale and maintained by the forces they had, not the forces they wished they had. This choice, made in the design offices years before the war, proved decisive once conflict began. The captured Allison, sitting in the Stuttgart workshop in spring 1943, represented the moment when German engineers fully understood what they faced. Not just another enemy engine to study, but evidence of an industrial system they couldn't match. The technical superiority of individual German designs couldn't compensate for America's ability to produce good designs in overwhelming quantities. By the time this reality became undeniable, Germany had lost the industrial war that would determine the shooting war's outcome. The V-1710's story is not one of technical supremacy or revolutionary innovation. It's the story of appropriate design, of engineering decisions made with clear understanding of industrial realities, of priorities chosen to match strategic requirements. The engine wasn't celebrated like the Merlin, wasn't legendary like the radials that powered heavy bombers, but it did its job, proved the philosophy behind its design, and helped win the war through sheer weight of numbers and relentless availability. When German engineers admitted they were 5 years behind, they weren't acknowledging that American engines were better in conventional terms. They were acknowledging that American engineers had understood the problem differently, had asked different questions, and had arrived at answers Germany couldn't match. The gap wasn't 5 years of development time. It was 5 years of fundamentally different thinking about what industrial war would require. That thinking, embodied in the robust simplicity of the Allison V-1710, gave America the industrial edge that no amount of German technical sophistication could overcome. The engine that seemed crude to German eyes was exactly what America needed it to be. And that insight, that understanding of how to match design to strategic requirements, was what Germany had missed and couldn't recover. The war would continue for 2 more years. But the outcome was already determined by decisions made in the 1930s, decisions that the captured Allison engine made visible to those who knew how to read what they were seeing. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.